Welcome back to our Algebra 2 series. Today we're up to section 2.6 where we'll be looking at complex number equations. In previous sections we've looked at complex numbers. It's made up of a real number and an imaginary being added together or subtracted. Here 2 is the real number and 3i is the imaginary number. Generically speaking, we can say a complex number is a plus bi, where a is the real number and b is the imaginary number. So let's say we have two different complex numbers, a plus bi and c plus di. And let's pretend that they're equal to each other. For this to be true, a and c must be the same and b and d must be the same. The real parts must be equal to each other and the imaginary parts must be equal to each other. So a is equal to c and b is equal to d. So here's an example. 3x plus yi is equal to 5x plus 1 plus 2i. So we need to solve for x and y. So before your head explodes, let's separate this into the real and imaginary parts. For the real part, 3x must be equal to 5x plus 1. We're only looking at the real parts of each complex number. So we can subtract 3x from both sides and 1 from both sides to give us minus 1 equals 2x, or x is equal to negative 1/2. If we look at just the imaginary parts, y must equal 2. So we've already solved for y. So by separating the equation into its real and imaginary parts, we can easily solve for the two variables. But what if we want to multiply two complex numbers together? It almost looks like we're multiplying two binomials together. So we can use the same FOIL technique. Remember, first, outer, inner, last. If we multiply the first part of each quote-unquote binomial, 4 times 7, we get 28. The outers together would be 8i, the inners would be 21i, and the last would be 6i squared, because it's 3i times 2i. So we can combine those all together, and then combine some like terms. Let's focus on this I squared. Don't forget, I squared is equal to negative 1. It's the definition of I. Therefore, this is 6 times negative 1, or it just becomes negative 6, which gives us more like terms to combine with that 28 over there, and we end up with 22 plus 29i. So let's look at this 4 plus 3i complex number and compare it to 4 minus 3i. This is what we call a conjugate. These are conjugates of each other when you flip the sign between the real and imaginary part. So here we have the generic a plus bi being multiplied by its conjugate, a minus bi. If you were to FOIL this out and multiply it all together, you would end up with a real number, a squared plus b squared. This almost looks like a difference of squares from our old algebra days, but instead we have a sum of squares. That is because we have an imaginary term here. When this I gets multiplied by itself, we end up with I squared, which is negative 1. So the sign ends up getting flipped. So we end up with a sum of squares instead of a difference of squares. But what good does that do us? Let's say we want to divide two complex numbers. The first problem here is we have an imaginary term in the denominator of a fraction. We need to rationalize this denominator. Remember, to rationalize the denominator, we need to multiply by y over y, which is just 1. In this case, we'll use the conjugate of the complex number that's in the denominator to rationalize it. The conjugate is just the flipped sign. So here we're still multiplying by 1. It's something over itself. So if you multiply across, the top becomes negative 14 plus 4i after we FOIL that out, and the bottom becomes 1 minus I squared. Remember, I squared is negative 1, so 1 minus negative 1 is 2, and we can factor that 2 out, and we end up with negative 7 plus 2i. As a side note, if you look at the denominator, we are multiplying a complex number by its conjugate. If we remember this formula, when we do that, we end up with a squared plus b squared, In this case, A is 1, but B is also 1. We can think of this complex number as 1 minus 1i. So if we substitute the A and B into this equation, we get 1 squared plus 1 squared, which is 2, which is what we ended up in the first place. So whether you use this formula or FOIL it out, you will end up with the same answer. Let's jump over to the whiteboard and do some examples. Never had one lesson. Alright, we're going to put an equation up here. 3x plus 1 plus, and we use some parentheses here, y plus 2i is equal to 2x plus 2yi. We want to solve for x and y. So before we do that, let's just isolate the real parts and the imaginary parts. So 3x is real, 1 is real, and 2x is real. So I'm going to draw a line over these and this. And these are the real parts. And the imaginary parts would be y plus 2 and 2y. So remember, when we have an equation like this, the real parts on one side have to equal the real parts on the other side. So let's just write that out. We have 3x plus 1, that's the real part on the left side, is going to equal the real part on the right side, which is 2x. So if we subtract 2x and add and subtract negative 1 from both sides, we end up with x is equal to negative 1. Now for the imaginary parts, we have on the left side of the equation y plus 2, and the imaginary part on the right side of the equation is 2y. So we'll subtract y from both sides, we get 2 equals y. So there we go. We found x and y in this equation that looked a lot more complicated than it really was. Now we're going to do a quick problem down here just as a little refresher. We're going to say 7i. What I want to do then is square this quantity. So what I'm going to do is rewrite this as 7 squared times I squared. And I like to make my i's bendy sometimes. All right? The 2 gets kind of distributed as the exponent. So this ends up being 49 times I squared. For I squared is negative 1. So 49 times negative 1 is negative 49. So when you have I squareds and exponents of I, be careful to look out for sign flips like this. All right, let's clean this off and then do a FOIL example. All right, we're going to go up here in the corner, try to save as much room as possible. And the first complex number is negative 2 minus 3i. And we're going to multiply that by 6 plus 5i. So we can treat this like a binomial, and we're just going to FOIL this out. So we'll start with our firsts. Negative 2 times 6 is, I'm on the screen, right? Negative 12. Our outers, negative 2 times 5i. That's negative 10i. Our inners, negative 3i times 6 is negative 18i. And then our last, negative 3i times 5i, would get us negative 15i squared. So we have some like terms here, so let's just write that out. Minus 12, negative 10 minus 18 is going to get us negative 28i. Now here, for this 15, what I'm going to do is I'm going to write negative 15 and then take the I squared and turn it into negative 1. Remember, these are the same thing. And we got to be careful of our signs here. It's easy to lose a sign here or there. So let's just rewrite that out. Negative 12 minus 28i minus 15 times negative 1. So this will be plus 15. So now we've got some real number here we can combine together. This becomes negative 12 plus 15 is 3 minus 28i. There we go. I'm going to squeeze in one more example down here. It's going to be 5 plus 7i. And what I'm going to do is multiply it by its conjugate. So all we did is flip the sign from positive to negative. Now remember, when we do this, we end up with a squared plus b squared. A would be 5 and b would be 7. So I think I can squeeze this in here. A squared would be 25. B squared is 49. If we add those together, we get 74. So we took a complex number, multiplied it by another complex number, which happens to be its conjugate, but at the end of the day, you end up with a real number. All right, let's run this off and do one of those fun division problems. Right, back up here into the corner. 2 minus 3i divided by 3 plus 5i. So we need to rationalize this denominator. We need to multiply this whole thing by some fraction that is something over itself to get rid of this complex imaginary part down here. So what we're going to do is use the conjugate. So we're going to take this 3 minus 5i. All we did was flip the sign over 3 minus 5i. We're allowed to do this because we're just multiplying by 1. It's something over something. And then we're going to multiply across. So we'll do our normal FOIL business here. So 2 times 3 is 6. 2 times minus 5i is negative 10i. Minus 3i times 3 is minus 9i. And negative 3i times negative 5i is a positive 15i squared. Again, a negative times a negative gets us a positive. We've got a sneaky I squared over here. And we'll draw a line like this. Now we're going to use this a squared plus b squared trick again because we're taking a complex number and multiplying it by its conjugate. So it's going to end up being a squared plus b squared. A squared, I'm just going to write it down as 3 squared, which is the a, plus the b squared, which is 25, 5 squared. So slide all this nonsense over here. We have 15i squared, which is going to be a negative 15. We're going to write this out. We're going to take the time to do this step. We'll combine these like terms. So negative 10i minus 9i is minus 19i. Now, 15i squared is 15 times negative 1. So this turns into negative 15. And then we're going to take this 3 squared, 9. I'll just write it out as 9 plus 25. So now we've got more like terms up here we can combine. 16 minus 15, that's minus 9 with the 19i. So we've got a complex number on top. And then 9 plus 25 is 34. We end up with a nice rationalized denominator real number at the bottom. And that's it for today. We'll see you next time.